Recently, many of us have seen videos circulating online of the sun's surface looking somewhat like a soup of yellow and orange bubbles threaded with dark lines that are shifting around. And what's really exciting is that these are the most detailed images of the sun that we've ever taken, and they show that the sun's surface is constantly moving. Using the Daniel K. Inouye Solar Telescope, or DKIST, located in Maui, Hawaii, scientists were able to resolve structures that were only tens of kilometers across. That's like being able to see a human hair from the top of the Eiffel Tower, the Empire State Building, or from the top of the Taipei 101 building with only the naked eye. But the real reason that these images are so exciting is because for the first time, scientists have been able to observe processes happening along the edges of these boundaries, something that's been predicted for decades but never conclusively seen. It's something called Kelvin-Helmholtz instabilities. So what exactly are we seeing in these images from the solar telescope? What exactly is a Kelvin-Helmholtz instability? And why might something that's happening at such a small scale matter for the overall activity of the sun? Hello, my name is Jeff. I'm a space physicist and a PhD researcher. I talk about space weather, planetary atmospheres, and how scientists can measure some of the regions and objects throughout space that we can't always see directly. So let's dive in. To start, what did scientists just discover on the sun? The sun's photosphere is covered in convective cells that we call granules. These are the yellows and oranges in all of the pictures that are circulating online right now. These bright bubbling regions are actually plasma rising up from the interior of the sun. As they spread outward, they cool off and they're able to sink again in a process that we call convection. At the same time, magnetic fields thread through that plasma, creating magnetic regions with boundaries where different granules can behave very differently. And the Daniel K. Inouye Solar Telescope, or DKIST, just uncovered something along those boundaries. It showed us tiny swirling structures and dark striations forming and evolving where regions of magnetic field build up and meet the surrounding plasma. The important part is that these structures were not isolated. Researchers found them repeatedly along magnetic boundaries, and their appearance matched structures that have been found in high-resolution models of the same environment. So DKIST actually just uncovered a very small-scale physical process that, until now, has been hiding below the resolution of our previous observations. Now, what is a Kelvin-Helmholtz instability? This happens when two fluids move past each other in opposite directions, creating what we call a velocity shear along the boundary in between them. If that shear becomes unstable, then small disturbances can grow into swirling, wave-like structures that begin to mix the two fluids across the boundary. We see versions of this in Earth's oceans and in its atmosphere, in the atmosphere of planets like Jupiter and Saturn, and along the boundary of planetary magnetospheres. But on the sun, there's another important ingredient. There's magnetic fields. In the region observed by the Daniel K. Inouye Solar Telescope, the magnetic fields were mostly vertical, while the plasma flowing around their edges was mostly horizontal. In this case, solar physicist models actually showed them the exact same kind of structures seen in the DKIST observations. And their wavelengths, their growth rates, and their motions were all very consistent with Kelvin-Helmholtz theory. So scientists didn't just see turbulence on the surface of the sun. They observed characteristic behaviors for a very specific physical plasma instability that we've expected to find there for decades, but until now haven't seen. All of this might lead one to wonder, can these tiny instabilities cause solar storms? Probably not directly, but they may contribute to the types of processes that build up into solar storms. As Kelvin-Helmholtz instabilities grow, they can mix magnetized plasma with less magnetized plasma and start to spread magnetic field throughout the surface of the sun. And this matters because magnetic fields that are rooted in the photosphere spread upwards into the sun's atmosphere. Disturbing them near the surface can influence how mass, magnetic flux, and energy are distributed up into the sun's outer layers. And these processes are relevant to questions like how the corona gets so hot and how magnetic energy builds up before solar activity. So this study doesn't show that Kelvin-Helmholtz instabilities cause solar eruptions, but it does show that previously unresolved physical processes are present around magnetic boundaries in the photosphere. And that does give solar physicists a new piece of the puzzle to understanding how processes at the sun's surface connect to its upper atmosphere. Every week on Heavy Brain Space, I break down new questions about how space actually works without burying you in large equations and heavy terminology. I'm Jeff. Thanks for hanging out. Cheers.